3I Atlas entered our solar system on a gravitationally unbound trajectory, traveling at a velocity of 57.95 kilometers per second. It is only the third confirmed interstellar object ever discovered. While initial speculation suggested an artificial origin, its movement is governed entirely by the Sun's gravity. It has shown no non-gravitational thrust or course changes that would indicate a powered probe. At 3.32 astronomical units from the Sun, the object began to outgas. Heat caused the sublimation of volatile ices, the process of a solid turning directly into a gas, which carried dust away from the nucleus to form a visible coma and tail. This velocity and trajectory suggest 3I/Atlas originated from the Milky Way's kinematically hot, thick disk population. This implies an age between 3 and 11 billion years, making the object billions of years older than our own solar system. The true mystery of 3I/ATS is a profound chemical anomaly hidden within its ancient volatile inventory. To analyze this chemistry, astronomers used the James Webb Space Telescope's Near-Infrared Spectrograph, or NIRSpec. They utilized its integral field unit, an instrument capturing a full light spectrum for every spatial pixel simultaneously. During a 640-second exposure, the telescope captured wavelengths between 0.6 and 5.3 micrometers as the comet moved through the inner solar system. This line graph shows the comet's integrated spectrum, plotted logarithmically. The broad maximum at 1.2 micrometers is sunlight scattering off dust grains, while the sharp spikes are the fluorescence of gas molecules. Because this integrated view blends every signal together, researchers had to mathematically extract these specific emissions to map them across two-dimensional space. To do this, researchers use polynomial continuum subtraction. This mathematical technique models the broad background of scattered light and removes it, isolating the specific wavelengths where only gas emission occurs. The isolated dust map at 1.2 micrometers reveals a bright, expansive cloud of solid particles extending across the entire field of view. When we isolate the 4.3 micrometer emission, we see the spatial distribution of gas phase carbon dioxide. The extreme brightness of this map indicates that carbon dioxide is the dominant driver of the comet's activity. Secondary maps for water at 2.7 micrometers and carbon monoxide at 4.7 micrometers are noticeably fainter, yet they confirm the presence of a diverse molecular coma. By subtracting the continuum, researchers transformed a single point of light into a multi-layered topographic map of the comet's chemistry. Comparing these maps reveals a structural difference. While the gas maps appear somewhat symmetrical, the dust map shows a distinct directional bias. Interpreting this is difficult because of a concept called 1/ρ dilution. In a vacuum, gas and dust expand quasi-spherically from the nucleus. As the distance, or ρ, from the center increases, the density drops exponentially, creating a uniform glow that masks the true outgassing patterns. Scientists correct for this by mathematically dividing out the expansion effect. This creates a 1/ρ enhanced map, stripping away the outer coma to reveal the inner physical activity. The enhanced dust map reveals a strong plume-like feature emanating toward the Sun. Higher temperatures on the day side of the nucleus cause more rapid sublimation. This localized heat launches and fragments dust grains specifically in the sunward direction. These differing patterns prove the comet's outgassing is heterogeneous, driven by localized thermodynamics rather than a uniform melting of the surface. To quantify this activity, we transition from mapping locations to measuring the apparent production rate, symbolized as Q. This metric represents the total number of molecules ejected per second. To calculate Q, researchers measure gas intensity in concentric mathematical rings moving outward. This chart shows production rates for carbon dioxide and carbon monoxide, leveling off at 3,000 kilometers, indicating outgassing is complete within that boundary. The red line for water behaves differently. It does not reach a clear asymptote, which means water is still being produced further out in the coma. This continued production matches the detection of a 3.0 micrometer water ice absorption band. It suggests that water is sublimating directly from icy grains that have already been pushed into the outer coma. These terminal production rates allow us to calculate the comet's overall chemical recipe and compare it to our own solar system. To compare comets of different sizes and origins, astrophysicists use the CO2 to water mixing ratio. This plot shows the mixing ratio for solar system comets, following a predictable low-sloping trendline. Plotted at 3.32 astronomical units, 3I/Atlas sits far above the local norm. Its calculated ratio of 7.6 is 18 times larger than expected. This is a 4.5 sigma deviation from the established rule. Only one peculiar local comet, C/2016 R2, has ever shown similar hypervolatile behavior. These numbers reveal that the chemical engine of 3I/Atlas is intrinsically dominated by carbon dioxide. It was built in a radically different environment. What physical conditions in another star system produce an ice rock so heavily dominated by carbon dioxide? One possibility is its native ice line, the boundary in a young protoplanetary disk where temperatures drop low enough for specific gases to freeze. 3IA Atlas may have formed in a narrow band where carbon dioxide froze easily, but water was depleted. A second hypothesis considers the comet's history in interstellar space. Billions of years of exposure to ambient radiation may have selectively altered its chemistry, suppressing water sublimation more than other volatiles. Because 3IA Atlas originated from the Milky Way's thick disk population, it likely formed around a star born billions of years before our Sun. At that early stage of galactic history, there were fewer generations of stars to enrich the galaxy with heavy elements, resulting in a low metallicity environment that directly shaped the volatile ratios we observe today. This 4-billion-year-old chemical time capsule provides more scientific utility than any structural debris. It allows us to reconstruct the environment of an ancient stellar nursery. By analyzing a single infrared data cube, JWST has successfully mapped the pristine chemistry of a distant star system, revealing if our own solar system's recipe is typical or a rare outlier in the Milky Way.